So we're going to follow up our conversation about aldehydes and ketones with a little bit more detail about oxidation. We really want to start to think about aldehydes, ketones, and carboxylic acids. So we're going to think about methane, methanol, formaldehyde, formic acid, and carbon dioxide all existing on this spectrum of oxidation states specifically for carbon. Notice the -4, -2, 0, +2, and +4 oxidation states. The first thing we're going to talk about today is drawing mechanisms for the formation of hemiacetals and acetals. So a hemiacetal is a molecule that contains an OH group and an OR group bonded to the same carbon. Hemiacetals are going to be the minor components of an equilibrium mixture, except where you can form a 5 or 6 membered ring, which is shown below. We talked in class about this idea of an acetal then being a molecule containing 2 OR groups bonded to the same carbon. So a hemiacetal, right, versus a diethyl acetal. And again, I can also have a cyclic acetal. So it's important that we talk about the mechanisms for how to form these molecules. So the first step is to add a proton. That proton is transferred from HA to the hemiacetal oxygen. Step 2 is to break a bond to give a stable molecule. And so remember, part of breaking bonds involves, can I form resonance stabilized cations? That's something that we've looked at before, specifically around SN1. The next step is the reaction of an electrophile with a nucleophile to form a new covalent bond. Finally, step 4 is to take a proton away. This is where proton transfer to A- gives the acetal and regenerates the acid catalyst. The formation of acetals is an equilibrium reaction and is reversible. So to form an acetal, experimental conditions are used that remove water as it's formed, thus driving the equilibrium reaction to the right and generating acetals. By manipulating the equilibrium, so if we use a large excess of water, then we can convert the acetal back to the original aldehyde or ketone. So one way to synthesize the hydroxyaldehyde that's shown on the right is by using a Grignard reaction. But first we have to protect the aldehyde of the bromoaldehyde before we can generate the Grignard. So one possibility is to use a cyclic acetal. Now the Grignard reagent can be prepared and I can form a new carbon-carbon bond. So notice, I form as my first step a cyclic acetal, then as my subsequent step I form a Grignard reagent, and then as the third step I form my magnesium alkoxide, which I can then protonate to generate my alcohol. So hydrolysis in aqueous acid will then give back my hydroxyaldehyde. Another reaction that we want to think about is an imine. This is a compound containing a carbon double bond to nitrogen. This is also called a Schiff base. So it's formed by the reaction of an aldehyde or ketone with ammonia or a primary amine. So for example, ethanol and aniline. But let's take a look at a simpler example. An imine, right, could also be formed simply by the reaction of an aldehyde or a ketone with ammonia and a primary amine. So we're going to look at an example of the mechanism for how to form these molecules. So first, we have the reaction of a nucleophile and an electrophile to form a new covalent bond. In this case, my amine is the nucleophile, which is attacking the carbon, which is the electrophile. That's going to then create an intermediate where the oxygen can transfer and take a hydrogen bond. The electrons from that bond can now come down onto the amine. I now have a tetrahedral carbonyl addition intermediate. I do 2 proton transfer reactions and I lose water, because water is a great leaving group. That is what allows me to generate the formation of an imine. Now the beauty of this is we're getting to the point where in the reaction mechanisms that you're drawing, there are multiple ways to do this. Now you might be wondering to yourself, why does the formation of an imine matter? Well, it matters because when we think about our site, one of the things we think about is 11-cis-retinol and a protein called opsin, and the formation of a molecule called rhodopsin, or visual purple. And what you can see from this diagram is a rod cell that has membranous discs, ciliary body, a cell body, and a nucleus, and then these transmitter vesicles. What ends up happening is that when light energy hits these molecules, they undergo a conformational change. That changes in membrane permeability, and that generates an action potential. And that's largely due to the reaction of retinol with opsin to form rhodopsin. And that's what allows us to see. Now, there are other reactions that we also should consider when we're thinking about aldehydes and ketones. That's reductive aminations. This is the formation of an imine followed by the reduction to an amine. So it's 2 steps. The first step is the formation of an imine. The second step is the addition of hydrogen across that double bond to generate an amine. So reductive amination is a valuable method for converting ammonia to a primary amine or the conversion of a primary amine to a secondary amine. Enols are another example of a molecule that we're going to look at. So these are molecules that contain hydroxyl groups bonded to a carbon of a carbon-carbon double bond. So the keto form is what predominates at equilibrium for most simple aldehydes and ketones, but it's worth taking a look that enol is a molecule that can exist depending upon equilibrium. So here we have several forms of the keto as well as the enol. You can actually see the percent of the enol at equilibrium to see that it's actually quite low. If we wanted to draw enol forms for each ketone, that would be pretty straightforward. So let's take a moment, do that, take a pause if you need to. Recall that the enol form simply replaces the ketone with a hydroxyl group and puts a double bond between 2 carbons. Can you then likewise convert the enol form back to the keto? When we think about the mechanism for this, the interconversion of keto and enol forms is catalyzed by both acid and base. So following is a mechanism for acid catalysis. The first step is the addition of a proton to the carbonyl oxygen. The second step is to take a proton away from the alpha carbon to form an A- conjugate base. So your conjugate base can take that proton. It's important to think about this because an enantiomerically pure aldehyde or ketone with at least 1 alpha hydrogen can be treated with a trace of acid or base. It will gradually become a racemic mixture and lose all optical activity. So it's really important that we protect ketones and aldehydes from exposure to acid or base unless we want to lose that stereochemistry. So aldehydes and ketones that have an alpha hydrogen can react with Br2 and Cl2 to give alpha haloaldehydes or alpha haloketones. That's a reaction that's shown here. We're going to take a step through that mechanism. So the first step is the formation of the keto enol. So this is what's referred to as a tautomerism, where I have my keto form and my enol form, and at any given time my molecule can exist in either of these forms. Step 2 is the reaction of an electrophile and a nucleophile to form a new covalent bond. So in this case, the electrons come down. The electrons from my double bond then act as a nucleophile to attack the bromide. If I think about the value of alpha halogenation, that's that my carbon now adjacent to an aldehyde or ketone bears a good leaving group, and that carbon is now susceptible to nucleophilic attack. So this is one way to build in complexity, where I have 2 simpler molecules that I can join together now because I have a great leaving group. So aldehydes are one of the most easily oxidized of all functional groups. Some examples are shown here. Ketones are not normally oxidized by chromium reagents. In fact, this reagent is used to oxidize secondary alcohols to ketones. However, I can oxidize ketones using nitric acid at higher temperatures, and that oxidation is typically through the enol. So for example, adipic acid is one of the starting materials for the synthesis of nylon. I can also reduce aldehydes and ketones. So aldehydes are going to be reduced to primary alcohols, whereas ketones are going to be reduced to secondary alcohols. So examples of that are shown here. And then catalytic reductions are generally carried out from 25 to 100 degrees Celsius and from 1 to 5 atmospheres hydrogen. And a carbon-carbon double bond could also be reduced under these conditions, so using hydrogen and nickel. And again, you don't have to know the mechanisms for these two examples, but you do have to be familiar with the starting materials and the products. So the most common laboratory reagents for the reduction of aldehydes and ketones are sodium borohydride and lithium borohydride. We talked about those last class. Both of these reagents are sources of the hydride ion, H-, which is a very strong nucleophile. That's what's shown here. So the key step in metal hydride reductions is the transfer of a hydride ion to the carbonyl group to form new covalent bonds, right, from a tetrahedral carbonyl addition compound. So that's what's shown here. Hydride adds in to my electrophile, kicks my electrons up, forming my O- complex. That then becomes protonated through a proton source such as water during hydrolysis. It's important to know the difference between hydrogens that function as nucleophiles and hydrogens that are protic or from proton sources. And it's really important that we're able to make this distinction because going forward, we're now going to look at carboxylic acids. That's our next step. Thanks again for listening. Have a great day.